Okay, let's gonna have a look to the MATLAB to the directory structure of MatConvNet. So the first thing to notice is that I have changed the version from beta 16 to beta 17 because there are quite a lot of interesting updates provided by Bedali and his team. But in any case, like the structure remains pretty much the same. So we have the MATLAB directory and session, which is the folder where we have all our materials, then some utilities, examples, and so on. So the important thing is within the MATLAB folder. Here we have like all the available layers. So we have like patch normalization, layer concatenation, so convolution transpose, cropping, dropout, different type of loss functions, normalization, LP norms, poolings, ReLU, sigmoids, softmax, quite a lot of basic building blocks, basic layers, and you can keep adding to these basic blocks. Then we have simple NN folder, which basically is the previous way people were working with MatConvNet. So before we moved to the DAG network, people were using the simple net to perform like the inference, to do training and everything. But let's gonna forget about this for the time being. In the source folder you have all C++ code and CUDA code, okay, to run convolutions and batch normalization and so on, calling to QDNN and CUDA. But we can also forget about this for the time being. So we are more interested in the DAGNN structure. So as we saw last week, DAGNN is now a MATLAB object. Okay, and the way you do objects or object orientation in MATLAB is by building this sort of folders, plus that represents a class. So within this class we have like several wrappers for the different layers. So here we saw like the actual way to call the layers, but here we have some wrappers for those functionalities. For instance, if we open the convolution one, like see that convolution is a class that inherits properties from the class called filter, okay, and it has size, bias, and some options. So those are three properties of member of the convolution class. Then it has a forward method, so this is going to be in charge of doing the forward pass, basically we're calling the actual MATLAB function BLNNCOM that we saw before, okay, with some parameters. We also have the backward pass to perform the backward propagation, and then some auxiliary functions like get kernel size, get output sizes, init parameters, and so on and so on. Okay, so this is basically object-oriented wrapper to have convolution working as objects. The same is true for the different layers: concat, batch normalization, spatial normalization, and so on and so on. This is the way we define the different layers here as objects. Okay. When we do DAGNN.comp, what we are doing is basically to call the initializer of the constructor of this object, this class, to create a convolution object. Okay, then we have the DAGNN object itself, and this is the important guy, because here is where the forward and the backward propagation takes place. So among the different functionalities we have here, we have the add layer, which we are continuously using here in order to add new layers to our network. We also have things like set layers input and output, do the printing of the net, something we did in the last session to see the structure of the network. We can also get the receptive field size, move from a simple NN, and so on. But probably the most interesting part is the evaluation code, which is in charge of doing forward and backward propagation. This code is not complicated. I will recommend you to read the explanation here, okay, because it sort of clarifies how back propagation works. Basically, you need to take in mind that you need to initialize the members that are going to be back propagated by assigning a derivative value. So, for example, like when you set objective 1, that means that the derivative of objective is going to be 1, so that means that's the end of the chain, and then you are going to be back propagated from the end backwards. But you might have like more than one layers with a derivative, so that means that you could start back propagation from 2 different places, and you might also have values different from 1. You might have values that are 0.6, 0.7, so those are going to be interpreted as weights. In any case, this is a more advanced functionality. What I want to show you right now is how the evaluation works, so forward and backward evaluation. Yeah, it's pretty much this code. So this is the forward pass, okay. What is happening here is that the inputs, which is this structure built by the getBat function we saw before, so this one here, this cell array consisting of a couple of strings like inputs and labels, and the data, images and labels. So the inputs, the first 2 field, that means the name of the field, in this case data, input, and the data itself, are gonna copy. Okay, so we're gonna get the indices. We're gonna get the names of the inputs, or we are gonna get the indices. If everything is okay, those indices are gonna be copied into the bars structure of the network. Remember that bars is where all the blobs are contained. So basically what we are doing here is to fill the first blobs with the input, and that's the way we are gonna start. So we just fill in the structure of inputs created by the getBat function into the first blob of the net, which represents the input. And this is what is happening here. So V is gonna be 1 probably, which is the first index, and deal is gonna be in charge of copying the cell array into the value field, and then we get rid of the inputs to save some memory. Okay, now we check how many pending variables are being referred. So basically, like if we still need to evaluate the network, and that is an information we can get from the fan out of the current bars. So basically the fan out is how many things are going out from the current module, so the connection of the current layers with the next layer. And in case there is still something to evaluate, we start looping in execution order. So Remember that when using DAG, our network can take the shape of a graph, and that means that we can have like strange things that are so we can have layers that are not directly connected. So layer 1 can be connected to layer 2, but it can be connected to layer 3 and layer 4 and so on. So that requires to define a sort of evaluation order, in order to have all the dependencies of the current layer fulfilled before running that layer. So we don't need to do anything about that because that's already defined in the execution order. What is going to happen here is that this will be like assigning or choosing which is the next layer to be executed. So once its pre-requirements are fulfilled, and then for that given layer L, so we access from the object is the network, layers L, block is the actual layer, so it's the object, for example convolution object or pooling object itself, and we apply the method forward advanced. So what is this? So for example, if we come to the convolution object, we see that we have the method forward and backward, but oops, not here. Sorry. Same layer. Sorry, yeah. We have the method forward and backwards, okay? But we also have forward advanced. So forward advanced is basically a forward method that allows you to do like more sophisticated things. So it allows you to modify it in order to do like new sort of forward computations and so on. But usually it's just calling the actual forward method at some point, the basic one, as you see here. So yeah, for us it's gonna be just the way we call the forward method. So the forward method of the layer is called, okay, we compute the forward time, so basically the time that took to compute to run the whole layer, and then we keep looping, like asking for the next layer to be run, and so on until we are done. So for the backward propagation pass, it's a bit more tricky. So in order to do the backward propagation, any of the derivatives has to be activated. If there are no derivatives assigned, we assume that we don't want to do backward propagation. Then in this case we need to start by copying the derivative outputs. So those derivative outputs are basically the derivative we assign at the beginning. For example, in our case here in BG train, that will be us assigning the derivative of the objective to be 1. We're gonna see that in the training code. But first of all, let's finish the evaluation code. So we have a set of derivatives, okay, and those are gonna be our starting points for starting the backward pass, starting from the last layer to the top layer, okay. So we copy that value to its appropriate place. So for example, if it's the derivative of the fourth blob we're gonna copy that into the fourth position, okay, of the bars structure. Remember that the bars structure is where all the blobs are. And then we start following the structure of the graph backwards. So we check if there are pending references to that blob, okay, and in executing order, in reverse executing order, we start applying the backward method to keep propagating the derivatives to the top until there is no more references to the current object. That means that there are no more links with the last layer. In order to better understand this from a theoretical point of view, what we are going to do is to have some special sessions showing how a DAGNN works in both its forward and backward propagation. But so far, I need you to understand the procedural way this is happening. So basically, this loop here that is like going from the last layers to the first layers, all the way calling the backward advance method. So basically taking the derivatives of the previous layer, computing the derivative of the current layer, and multiplying that with the derivative of the previous layer and propagating that like forward again, so to the top of the net. Okay, this explanation wasn't for free. We are sort of now ready to do some debugging here. So in the forward pass, we can add a couple of lines as I find in the script. Now that are going to allow us to check what's going on and where things are failing. So basically we're trying to see the parameters of the current layer, okay, so that's why we skipped the semicolon, and the size of the input for the current layer. Okay, so we are accessing the blobs of the network, and we're going to access the blobs in the position indicated by the inputs of the current layer. So if this is the current layer, this is the input to the current layer, so this is a reference to the blob that has to come into this layer. We take this to reference the appropriate blob, and we get the value of that blob, which is a tensor, a multidimensional array, and we want to know the size of that multidimensional array, because before what we were getting was an error message saying that the data reaching a specific layer was like smaller than the convolution filters. We didn't know which layer was that, and we didn't know about the size of the data or anything, so we're going to try to get that information now. Okay, let's see what's going on. Okay, work down again. So yeah, pooling window is large on the data, so apparently is been having problems in a pooling operation. So if we follow this, we see that it runs relu 5 from when it's trying to run pool 5. This thing is not big enough to do the pooling. So this output is basically the output of this first line. Okay, this first line, so the layer we're calling, and this second line is producing this output, which is this data size. And we see that when we reach pool 5, our image is 1 by 1 pixel. So So we have the 100 images defining our mini batch, as we specify here. 100 image of batch size. We have the 100 images defining our mini batch, composed by 256 channels or feature map, and the spatial dimension of the image are 1 by 1. Okay, but this is not big enough for our pooling 5, because pooling 5 has a spatial windows of 3 by 3, so we're not gonna be able to apply pool 5 here. So mainly this is due to the fact that we're using CIFAR10, while this network is thought for ImageNet, and ImageNet images are much bigger than the images contained in CIFAR10. So what if we try to solve this problem by adding some paddings to the first layer? Okay, so what if we, I don't know, we add some like 50 new rows from the top, 50 new rows to the bottom, 50 to the columns to the left, 50 columns to the right. So basically just adding some 0 padding here, and we try to run it again. Okay, now we got the error in a different place. So convolution 6, before we got in the error in pooling 5, now we move to convolution 6, and we see that our image size is 3 by 3, while convolution 6 has size of 6 by 6, so it's not big enough to apply the convolution. Yeah, so we can keep playing until we get like the correct padding here, which, if I'm not wrong, is something like 100. And we can see how images are getting smaller while they go through the network. And yep, now it's working. Yeah, we're finishing like the first mini batch of epoch 1. Yep, it's working. So in this way, just by having a very like little knowledge about how the evaluation function work, we were able to debug the problem, checking the input sizes, checking the current layer. So it doesn't take too much to actually modify this code and to debug this code. It's basically 2 loops, one going from the top to the bottom of the net, and the other one going to the bottom to the top of the net, or one going from left to right and the other one going from right to left. One is working on the blobs and the other one is working on the derivatives of the different layers. Okay,